Today we're going to continue looking at integration. Remember, our big idea for integration is that integration is multiplication, but one of the factors is variable. So that we have to drop things back down to integration is addition. And we want to think of integration as a continuous sum. We're adding up an infinite number of infinitely small things. That's too much infinity. But we can see that in the Riemann sum, which is why it's kind of strange that I never asked you to write these Riemann sums, but there it is. So we can imagine what we're trying to do is find the area under the graph of f and above an interval on the x-axis. We want to use area is equal to length times width, but the length is continuously variable. So what we do is we say area is length times width, and I just make the length constant for some small change in the width. So this f at xi delta x, the part that we're going to end up integrating, this is just area. We're just saying area is equal to length times width. So area So we're doing area equals length times width, but the length is the function and it's variable. So what we do is we assume that the length is constant for some small change in x. So area is equal to length times width, but the length is variable. We want to just multiply length times width, but we can't because the length is variable. So what we do is we break the area into small pieces. We assume that the length is constant for some small change in x. So that's the first stage. We want to use multiplication, but length is variable. So we assume length, which is the function, is variable. So we assume length is constant. For some small change in x. Because if delta x is small enough, then the function is continuous, then the function isn't going to change that much. Now that we can use multiplication, since we're assuming that the length is constant, now we can use multiplication, but and then we have to add up all of the rectangles. Once length is constant, we can use multiplication to get the area. So once length is constant for little delta x, we can use multiplication to find the area of a rectangle. And I usually phrase it, we get to use multiplication. And this is where multiplication becomes addition. We could, if the function was constant for over the entire interval, then we would use multiplication for the whole thing. But now we have to use multiplication in little pieces. So then we just add up all the areas, and that's what the sum is. Integration is multiplication, but one of the factors is variable. So we assume things are constant, so we get to use multiplication, and then we use addition to add everything up. So that's what the sum means. And then calculus comes in and says, now just use an infinite number of rectangles that are infinitely thin. So that's the limit as n goes to infinity. And now we're doing calculus. Then the big conclusion is that we start writing the integral from a to b of f of x dx. That's our continuous sum. And the amazing bit is that we can find an antiderivative and plug in the endpoints. All the extra stuff that we've been looking at for the definite integral part. All comes down to just using multiplication, but one of the factors is variable. So we assume that that variable factor is constant so that we get to use the multiplication. That drops us back to addition. And then we go from a discrete sum. We go from our discrete sum to the limit as n goes to infinity, a Riemann sum, a continuous sum. And we know that that results in a definite integral. And that's the boundary that we cross when we step into calculus. We start looking at infinity in a rigorous way. Any questions? All right. The tricky part of the class is not the calculus. The stuff that the problems that we've done ever since we started doing the applications of integration, the tricky part of all those problems is not the calculus. Because if you would recall, I stopped using the calculus portion of things. We spent a whole like 3 weeks learning techniques of integration. And then I just started bypassing it once we started setting up the integrals. We just started bypassing the whole integration thing. We set up a definite integral and we use a machine to calculate the rest of the definite integral. This is because it's 21st century, but math is always a little bit behind, so we use a machine from the 90s to do it. So the idea is that we have to use analytic geometry to set up the definite integral. Let's look at some more examples. Let's consider a region. And once again, we want to set up a definite integral. The goal is to set up a definite integral that will tell us the area of the region. Let's say the graph. Let's find the region, the area of the region bounded by the graph of y equals the square root of x, the x-axis, and x equals 9. I think what I really wanted to see is if this highlighter will show up. Oh, it actually kind of does a little bit. So this is an old problem. We want to see how the old problem fits with our new thinking. We know that we can calculate this area by just integrating from 0 to 9 the function y equals square root of x. So we know that the area will be the integral from 0 to 9 of the square root of x dx. We can even calculate this by hand because we can just add 1 to the exponents and divide by the new exponent. Or we can math 9 the whole thing. Math 9, the square root of x with respect to x from 0 to 9. 18. No surprises there. So we're not surprised that we got an integer because the integral is going to be an x to the 3/2, which is really just a square root, and we're doing the square root of 9 and a square root of 0, so it's okay that it comes out to a nice rational number. When we set up the integral this way, we are slicing vertically. What we are doing is we are assuming that the length is given by the value of the function and using that value for some small change in x. And then let the fluorescent dry, so the orange is getting all smeary. So this was the setup that we used to set up this integral. Might not have been the actual setup that we used if we were doing the problems. When we were first learning the problems, we were just saying, book says, write this integral, and this is how it'll work. But now we're getting into more details. Let's look at the details. This point on the graph corresponds to an x distance. X is always the distance from the origin, the horizontal distance from the origin to the slice. And y is the vertical distance from the origin to the point on the graph, not the slice. Well, the point where the slice hits the graph. We're trying to find an area, and area is always length times width. Area is equal to length times width. We're setting up a slice delta with a delta x for setting this up to work for small changes in x. And so that's our width. Delta x is our width. And then our length is the y that keeps changing. And y is determined by x. So the length is y. The width is delta x. And the way that we have to write y in terms of x, the same way we were having to write the radius in terms of the h in the problems yesterday. And we know that y is equal to the square root of x. So the area is equal to the square root of x times delta x. Now we're at this point. Once length is constant, we get to use multiplication. Here's the length times the width. Then we do this for a bunch of different values of x. Evaluate the function at n different values of x, and that's what leads to the Riemann sum. That's where we'll be at the sum as I goes from 1 to n. We're going to add up all these square root of x times delta x. And then we apply calculus. And we use infinitely many values of x. and that leads to our definite integral. That was the thinking that's sitting behind this calculation. We know that we can just plug things into our definite integral, but we don't want to think in those terms anymore. We need to be more mindful about where things come from. In this case, we slice this region up in a delta x way, but this is not the only option that we had. We also want to be able to slice things up in a delta y way. From a practical standpoint, it might be the only choice that we have. From a knowledge standpoint, we shouldn't argue against knowing a thing. We've already classified all the forbidden eldritch knowledge, so it's not going to show up in a calculus class. We've gone over all the forbidden topics as a faculty and said, well, they shouldn't know these eldritch things, so let's just stick to the calculus and we'll be okay. So maybe I'll just leave the eldritch stuff to my Patreon supporters. I'm just kidding, I don't have Patreon. So let's set this up. Instead of slicing delta x, slice horizontally so that the length is going the other direction. So now I'm going to set this up so that the width is delta y. I'm just calculating an area, and the only area we need in calculus is length times width. So here's our width, it's delta y, and here's our length, L. I still need to mark where x and y are. Y is this vertical distance from the origin, and x is this horizontal distance from the origin. Now we need L in terms of x, but it's starting from the same place. Area is equal to length times width. The length I've labeled on the picture as L, and the width is delta y, the delta variable that's in play. But now I need to write L in terms of y. But notice L is a horizontal distance so far in terms of x. I can write L, since this piece is x and this piece is L, and x and L is equal to 9. So since x plus L is equal to 9, I can say that L is equal to 9 minus x. Total is 9, one piece is x, the other piece is 9 minus x. But this is not what we want. We need L in terms of y. So I can write this as 9 minus x times the delta y. But I don't want the length in terms of x, I want the length in terms of y, and so that's we'll use the fact that y is the square root of x, so x equals y squared. So now I can write the length as 9 minus y squared. The width is still delta y, and now everything's in terms of my delta variable, just like we want. Then, just like before, we add up, when we make this calculation for n different values of y, make the calculation for n different values of y, and then add those up. So we take the sum as I goes from 1 to n of this area, 9 minus y squared, times the width delta y, And then we just use an infinite number of rectangles. We know that this will turn into, this Riemann sum becomes a definite integral. We just have to integrate over all the values of y. The y values start here at 0. Partially because mainly because we're on a coordinate system, and that's how we define this boundary by this function. So we need to set up an x and y coordinates. But also remember, wherever you define your variable, one end is the slice, the other end is 0, and the slice is in the positive direction. So it still fits with this description that we had before. What we're doing when we define our variables, like we were defining yesterday with the height, we are setting up where 0 was. We are setting up a coordinate system. Then we just have to end with the last value of y, which happens up here at y equals 3. So our integral is the integral from 0 to 3 of 9 minus y squared. Delta y becomes dy, which hopefully is also going to give us 18. Let's find out. So it's math 9 minus y squared with respect to y from 0 to 3. Also 18. Love it when a plan comes together. Any questions? Comments? Snide remarks? So this is just a review. This is taking a step back from the problems that we were looking at to look at simpler problems to reinforce, to make sure that our thinking is still working in the same way. That's the big idea. The thing I care about is how you think about integrals. In this particular problem, the last thing I care about is getting the area of 18. Even though, if I was grading this problem, it's the first thing I would look at. The first thing I would look at when I'm scoring a problem like this is I would look at the 18. If the 18 is correct, then I just kind of like scan through the definite integral that you set up. That's the thing I care about. And then I go back to how you set up your picture. So I look to see that if things are labeled properly. So when there's a problem in your answer, so if you got something other than 18, I would look at your definite integral. The first thing I look at in the definite integral is the endpoints, the interval over which you're integrating. Is 0 to, did you get 18 because you integrated from 0 to something else, like 0 to 9, because you're defaulting in the x direction. If your interval matches the variable you claim to be using, then I look at your function and I go back through your setup to see where the setup is. The number one thing that people get stuck on is I look at an integral and I look at the picture that's been drawn and it's just not labeled. There's a picture because y'all saw me draw a picture, but then you don't label where X and Y is. That's the number one thing. You just don't label where things are. Or you draw a slice in the wrong place, or you draw the slice in the right place and then for some reason label L over here. So what's happening when you're doing those things is that you're just trying to imitate the things that you've seen me write down. So you're just trying to imitate the things. You're just trying to mimic the incantations and the scribblings to try to make the magic happen. But there's no magic going on. We're just being careful about how we label things. And that's why I like to go back to these old problems to make sure that we talk our way through how these labels come about, where all these things come from, because it all means something. No mysticism here. You know what I mean? It's like people with like they look for the mystic powers of numbers, and there just aren't any. If you see a pattern, it's because you were looking for a pattern. If you go looking for a pattern, you will find a pattern. Some people get the wrong message from things like that. They watch the movie 23 with Jim Carrey, and they say, wow, does 23 have some secret powers? Like, oh no, the movie is not about the secret powers of the number 23. The movie is about Jim Carrey, I can't remember his character's name, going crazy because he started looking for a pattern, so he found one. And he was totally cheating when he was setting up all the 23s he was looking for, because sometimes you start adding up the dates, the digits in a date. Sometimes you use the century and sometimes you don't. Like, it was convenient for him to use the 2000. He needed to list the date as 2001 to get the 23. But when he had something from the 20th century, he was like, oh, I can't use the 19. That throws off my 23. It didn't fit the pattern, so he dismissed it. If you look for 23s everywhere, you'll find them. You'll ignore all the other numbers just to pick your 23s. So some people see the mysticism in the number 9, because if you add up the digits, like 0, 9, 1 and 8, 2 and 7, 3 and 6, 4 and 5, 54, 63, I lost track, 72, 81, 90. They all add up to 9, and like the 10s count up and the 1s count down. This is not fancy or mystical. It's just because 9 is 1 less than 10. And for clarification, yes, I integrated from 0 to 3. It goes up from bottom to top. So from 0 to 3, because the y values go from 0 to 3. In the previous calculation, we integrated from 0 to 9 because we were integrating dx. So the x's go from 0 to 9. Any questions? Comments? Snide remarks? Actually, thank you for the demonstration of why I have to stop and talk about nothing for a while. If I just started talking about another math class, we would not have had that clarification. But if I sit there and talk about nothing for a while, there's going to be something bugging you about, something will be bugging you about this problem. It's like, oh, wait a second. I'm not quite sure what it is. So if I sit there and babble for a while about nothing, then you're like, oh, wait, I know what it is. Why 0 and 3? And then we can clarify. See, it's all carefully manipulative strategy, carefully planned manipulative strategy. Well done. Plus, it's fun for me to talk about math, and I need to stop and let y'all get questions in. Otherwise, I'm just like, I'll talk forever. You know what I mean? And like, you're all like, yeah, we've had like 9 weeks of you, so we know exactly what it's like. Please make it stop. All right. So that was a little bit of a review, going back to some problems that we definitely have known how to do for a while. But really going into I wanted to go into the thinking that goes behind that calculation. Integration is multiplication, but one of the factors is variable. So integration is addition. You'll see this also as accumulation. The calculus portion is we are calculating a continuous sum rather than a discrete sum. we're trying to add up all the values of the function between 0 and 9. But because it's continuously changing, all the values doesn't mean anything. Or it means something really weird. But that's what we're studying in calculus. That's the whole point. Calculus is about infinity. Any questions? Comments? Snide remarks? All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.